Okay, so therefore, the proof of this theorem has been proved modulo A and B. So our next goal would be to prove A and B. Okay? So let's try to do that. Now we claim that A and B can be proved one go, provided we show this boxed thing here. What is that? That says, take any non-negative integer n and any positive numbers x1, x2 up to xk. The joint probability that x1 tilde is bigger than x1, small x1, x2 tilde is bigger than small x2, all the way up to xk tilde bigger than small xk, and n t naught is equal to n, this joint probability is equal to the marginal probability of n t naught equal to n and the product of the probabilities e power minus alpha xj. Okay. If this happens, let's call it star, then A and B would hold. So let's first show that, and then we'll show star. Okay, that's how we'll prove this theorem. So why is it true that star implies A? In order to show A, which is just showing that xi is a IID exponential alpha, you just sum both sides of star for all values of small n. Okay, just sum both sides of star with for all non-negative integers small n. You get that the joint probability, this joint probability is equal to this number. Of course, this immediately shows that, so remember that each of these are survival functions of exponential alpha distribution at the points x1, x2 up to xk. So therefore, it immediately shows that x1, x2 up to xk are IID exponential alpha. Okay. And then, since k is arbitrary, it actually shows that for all k, for all positive integer k, x1, x2 up to xk are IID exponential alpha, and hence the whole sequence is IID exponential alpha. Okay. So this shows that these are IID exponential alpha. Now, what you do is now you put this value here in star. Okay. Once you put that in star, so if you combine star with 1, you'll immediately get that this sequence xm is independent of nt naught. Well, you actually get x1 tilde, x2 tilde, all the way up to xk tilde. This vector is independent of nt naught, but that's enough to show that the sequence is independent of nt. So this shows that all we have to now prove is star in order to prove this theorem. So this proof of star is going to be a slightly longish calculation. So let's start doing that. So remember, star is just this identity. So just remember what are x tildes. So you fixed a point t naught, time point t naught, is this big red dot, and then s n t naught was the last phone call before time t. This was the first phone call after time t, so arrival time of the first phone call after time t, that is. This is the arrival time of the second phone call after time t, I mean t naught. Okay. So this is the time t naught, this is the arrival time of the last phone call before time t naught. This is the arrival time of the first phone call after time t naught. This is the arrival time of the second phone call after time t naught, and so on. Okay, and then these were the x tildes as shown in the picture. So we have to find the joint probability as given here. Let's just write down whatever every item means. So for example, x1 tilde is just the difference of S n T naught plus 1 minus T naught. Let's put it in. X2 tilde is just S of n T naught plus 2 minus S of n T naught plus 1. Let's just put that as well. And so on. Let's put all the values in there. Now, of course, this looks very complicated, but it's not so, because nt is equal to n. So wherever we see nt naught, rather, whenever we see nt naught, we can just replace it by small n. Okay, so let's do that. So by doing that, we get this probability is equal to this probability, which is Sn plus 1 minus T naught bigger than x1, Sn plus 2 minus Sn plus 1 bigger than x2, all the way up to xk here, and then nt naught equal to n. So things simplify because of strategically using this nt naught equal to n. Okay. Now observe that the successive differences are just x's. So this is just Sn plus 1 bigger than T naught plus x1, xn plus 2 bigger than x2, because Sn plus 2 minus Sn plus 1 is xn plus 2. Similarly, this difference is just xn plus k. So all of these are replaced by x's, and nt naught is equal to n. So the last step follows, because every Sm is equal to Sm minus 1 plus xm. Okay, so now let's go to the next page. We'll continue this calculation. So what we have achieved so far is this. We have been able to write the left-hand side of star as this probability, this joint probability. Now we are going to try to compute this joint probability. But I must say that this looks a lot less scarier than the initial one, which had random indexing involved there. But because the randomness in the indexing has been replaced by small n, the nt naught, namely the mt naught, things look much, much simpler now. So the next step is to write, see everything, okay, so before we go further, see here everything is in terms of Sn and Xn, right? Sn plus 1, Xn plus 2 and so on, which are continuous random variables, except one which is discrete. So whenever you have a mixture of, you have a probability which has intersection of some things which are continuous random variables and one which is discrete, it's harder to compute. So it's better to write everything in terms of one of them. And the way to do that is to observe that nt naught equal to n happens if and only if nth arrival is less than or equal to t naught, and the n plus 1th one is bigger than t naught. So let's put that in. So everything else remains the same, only this part becomes this. Now let's try to arrange things. This is same as saying Sn less than or equal to t naught. However, Sn plus 1 strictly bigger than t naught is already taken care of, because Sn plus 1 is strictly bigger than t naught plus x1, which is strictly bigger than t naught. So therefore, we don't have to keep it. It's redundant. It's already there. And the rest is as usual. So all of these are going to remain as usual. Now the next step of the calculation would be to write everything same, except just write Sn plus 1 as Xn plus 1 plus Sn, and then take Sn on the other side. So namely what becomes is, everything else remains the same. This part, Sn plus 1 bigger than t naught plus x1, is replaced by Xn plus 1 is bigger than t naught plus x1 minus Sn. Now why do I do that? This is done because we are now going to condition on Sn. That's why this is done. Okay. So what will be done is, this is something very similar to one of the calculations we did in the first lecture. You just fix Sn equal to u, or well, Sn very close to u. So that's the conditioning. Then everything here would remain the same, except that Xn plus 1, this Sn will be replaced by u. So that is what happened. Now then, of course, you have to uncondition, and therefore you have to multiply by the marginal of Sn, marginal density of Sn. And since Sn is less than or equal to T naught, you have to integrate the whole thing from 0 to T naught. So this is essentially, again, another continuous analog of law of total probability. Okay? And this justification can be done in a similar fashion as that justification of question mark that we did in the first lecture. So I'm not going to justify it anymore. It's something that can be justified, but you can just do it yourself, or you can just assume it to be true. And intuitively what we are doing is we are fixing Sn to be close to U, so that in this one, Sn is replaced by U. And then, since we are conditioning on Sn, we have to uncondition by multiplying with the joint density and then integrate in order to compute this, in order to account for this particular event, we have to only integrate from 0 to T naught. Okay? Since Sn is less than or equal to T naught, we will only integrate from 0 to T naught. So that will give us this expression. So then, what we have achieved so far is we have been able to write the left-hand side of star as an integral. And now let's use the independent structure. So note that Sn is just a function of x1 to xn. It's a sum of x1 to xn. And these are x's which are after xn. Okay? Xn plus 1, xn plus 2, and so on. So therefore, the entire thing is independent of Sn. So I can completely get rid of this conditioning. So this is just the unconditional probability here. Now note that xn plus 1, xn plus 2, xn plus k, etc. are independent. Okay. So remember, all the xi's are IID. So therefore, this just becomes product of the marginals. And we also know what are these marginals. We'll put the values in there. But just to tell you once more that we have used that Sn, which is just a function of x1 to xn, Sn, xn plus 1, xn plus 2, all the way up to xn plus k, these random variables are independent of each other. We have used this crucially here. We haven't used the fact that these guys are exponential alpha and Sn is gamma, parameters n and alpha. We'll use it in the next step.